All right, guys, it is August the 11th, 2020. We are in pulmonary mechanics. We are in pulmonary mechanics, RT210 D. We're going to get started. Not many people here in class today, but this is the recording. This is the lecture, which will start on time as much as possible. All right. Yesterday, we left off on dealing with volumes and minute volumes. We talked about minute ventilation, how much gas is moving between in and out of the airway in a minute, okay? Today, we're going to hone in on those things that we talked about by first going over this spirogram quiz on the board. We're going to give you some time to work on those, and then we're going to answer them, okay? Over the night, you should have studied the spirogram. Remember the spirogram in box form or the spirogram in wave line form. We talked about the 4 volumes and the 4 capacities, all right? So if you studied that, you should be able to draw the spirogram box style at least. Okay, you should have that down packed. That way, when you take your exam, you get your blank piece of paper, you can go ahead and write that spirogram down, and you are, when you have to refer back to it for the questions, you'll be, in good shape. So we're going to start off by going over these on the board, okay? This is what we have on the board. Number 1, 2, 3, 4, 5, and they are. Number 1 is tidal volume, or VT minus IRV equals. Number 2 is TLC minus VC equals. Number 3, notice the parentheses, FRC minus the RV, parentheses, right, plus tidal volume plus IRV. What would that leave us with? Number 4, VC minus IC. What would that leave me with? And finally, number 5, TLC minus IRV minus FRC. What would that leave me with? Best way to do these like this is to draw the spirogram box. Okay, Judith? If you draw that spirogram box, you shouldn't have any problem. You just take a piece of paper and cover up the ones that you're subtracting, right? You say, okay, this one, take away that one. That's what it leaves, okay? Very, very good tool or a way of working those out, okay? Very vital that you know the spirogram. You must understand what the volumes and the capacities or abilities of the lungs to do, and where are those volumes found? Which one of the volumes are most important, right? Which one of the volumes can we not access? Again, work on these now. I'm going to give us some time to work on these. I don't have anybody in class except for one student, so it'll be me and her. She'll work on those. I'll give you time to work on those at home when you're looking at this, this recording later on. I'll give you some time. I'm going to pause recording while you work on that. So go ahead and write that down on a piece of paper, those questions down, or pause it, pause the video, write those questions down, and then I will come back and go over each one. And then we got to move on to the next work that we're going to work on. We have to solidify the 4 volumes and the 4 capacities to get past pulmonary mechanics. It's all about the mechanics, right? We learn the ins and outs of the car, right? We learn the parts of the car, right? We learn the tires, the wheels, the steering wheel, the seats, and the body, But now, the mechanics of it is totally different. How does that car run, right? You can know all the parts of a car, but don't know how it runs. How does it function, right? What are the mechanics of it? So that's the same concept with our lungs. What are the mechanics of our lungs? We know we have 2 lungs, and we know each lung has, the right lung has 3 lobes, and the left lung has 2 lobes and a lingular section. We learned that each lobe has its own segments, right? We learned about the tracheobronchial tree and where they go in and out of the lungs. And yesterday we learned that the lungs are all about pressure, right? We learned on inspiration, there's a negative intrapulmonary pressure. And on expiration, there's a slightly positive intrapulmonary pressure, right? And so that's the mechanics. And so when I breathe in and breathe out, what is actually happening? How much of that volume is actually reaching my alveoli? How much of that volume is actually participating in what? Gas exchange, right? Don't forget that all of the airway from the nose all the way to the conducting, the respiratory bronchioles, right? Gas exchange starts in the respiratory bronchioles. So the last port or the last bus stop before you get into the land of the respiratory bronchioles, also known as the parenchyma of the lung, are the terminal bronchioles, right? You get off the bus at the terminal, right? If you ride a bus and keep on riding, never get off, you're gonna have to get off when they arrive at the terminal. That is the conducting zone. It's like a bus. It conducts you to this part of town, to that part of town, back over here, back over there, but that's all dead space, right? Only the gas that makes it to the alveoli is considered magic, right? That is the only part that's actually taking part in gas exchange. So we got to know what that volume is. How do I find the total volume in and out, right, per minute? And how do I find out what's just in the alveoli? And then when I know that, I can then find out how much of that volume or that total volume has been lost to dead space, which is dead space minute ventilation, okay? So this is the mechanics. Very, very important concept, guys. You got to know this to move on to the next section, all right? Work on these, and I'll be back with you in a couple minutes to go over. This is a closer look for those, back on the recording, for those who are looking, going to be looking at the lecture later. This is a closer look for you guys for the problems we're working on right now. 1, 2, 3, 4, 5. So students are now working on them. So you can pause your video if you're watching it tonight at home. Pause your video, write the questions down, and try to work them out before you push play and hear the answers, okay? Try to work them out on your own. Again, the best way to do these is to draw the spirogram box, the box form. You can do that. You should be able to do these with no problem, okay? All right, pausing again for about another 5 minutes, and we're going to go over. All right, guys. 1 through 5, we're going to have to go on now. Let's go over them. Okay. All right. Now, this is how you figure these types out. When you have these types of problems, again, I said it's best to remember or memorize how to do the spirogram in box form. Then you can kind of just cover up what it's telling you to subtract to see what you have left, okay? Or if it's saying this plus this, you can understand, okay, well, this box plus this box is this, right? That's the best way to do these, all right? So I'm going to draw the box over here. This one do not disturb. All right, I'm going to draw the box. PLC. I'll make a box. All right, I can go ahead and make my line right here because this is PLC. Then I always do, well, that's what I do. I always do tidal volume first, okay? So I'll put a VT right here, right? Above VT is IRV. Below VT is ERV, and then RV. All right, so I'll go ahead and make my little lines like that. Okay? Now, IRV plus VT is my vital capacity, right? So I'm sorry. IRV plus VT is inspiratory capacity, IC, right? So I'll go ahead and put IC right here, and this will be that. IRV plus VT is IC. ERV plus RV is what? ERV plus RV is FRC. It's FRC. All right. Now, the only thing left I have is vital capacity. That's everything you can do. So you'll have to, sometimes you'll have to, you remember that you still have this RV here. So a lot of times you'll do a little dot like that because this is still RV over here, right? So this is vital capacity. Everything you can do is vital capacity. Now, depending on how many colors you have, it's good to do it in colors. Okay, so let's say if I do vital capacity in red, and remember that vital capacity is everything that what I can do. All right, so this would be see that? Vital capacity. I want to do that because that lets me know vital capacity encompasses all that. See that? Colors will really help you make it pop. Okay. I'll try to put this a little closer for the guys for you guys that are online. Colors really help it pop. I don't know how good y'all can see my colors, but all right. So if I did vital capacity as red, right? So my vital capacity, and then we go, let's pick blue. Let's do inspiratory capacity as blue. Okay. So what I would do is I'm gonna do inspiratory capacity as blue. And I just put a little blue around my IC, and then I will put a blue line right here. See that? See that? That will be my inspiratory capacity. That's how you separate them. Okay, that way, if it's easy for you to know colors, you can separate them in colors. And then finally, FRC, let's do it in green. We'll say FRC in green, so I'll put a little green around the FRC and then make green. Some of them, some of them encompass others. Okay. FRC is my ERV and my RV, that whole green box, right? And then IC is the whole blue box. VC is the whole red box. And then TLC, which is black. Well, as a matter of fact, I'll do it in pink or whatever. We'll say TLC in purple will be the whole shebang. You can really get creative with your spirogram box. Whatever makes you remember how to remember it best, it's good for me, okay? So now that I have that understood, you have to memorize this spirogram. That's just the bottom line, all right? We started at 1 o'clock on these problems, so now we have to go over because we got to go on. Number 1. Tidal volume plus IRV. So let me give me a folder, and this is how I would work. Who was that trying to get in? Because it went away. Try it again because it went away. All right, so if I'm going to work on this, number 1, let's see, yeah, tidal volume, VT plus IRV. So let me look at it. VT plus IRV is all of this, right? This whole little box. So what's the answer? VT plus IRV is this. IC.
I see.
Good. So number one is inspiratory capacity. Number two, now, this is where the folder comes in handy. Number two says TLC minus the vital capacity. Well, I know TLC is the whole big thing, right? So let me take out the vital capacity part. Vital capacity is the red in here, right? So if I take out vital capacity, what's left? RV. See that? RV. Number three. This is the one that has a little bit more. I always work what's in parentheses first. FRC minus RV in parentheses. So let's do that first. Everybody look up here. FRC is the whole green, right? FRC. If I take FRC and take away the RV, FRC, take away the RV, what's left in FRC? ERV. Okay, so that's where we started. FRC minus RV in parentheses is ERV. Okay, so now ERV plus tidal volume plus IRV. So what is all of this? BC. BC. But that's a two-step problem. You do what's in parentheses first. FRC minus RV. This is FRC in green. Take away the RV. Only thing left in green is the ERV. All right, so this right here becomes ERV. So ERV plus VT plus IRV is all of this, right? All of this, which is the vital capacity. So that answer is vital capacity. You good, Miss Amy? You good? Okay. That is my vital capacity. Number four, vital capacity minus the inspiratory capacity. So let's look at it. Vital capacity. All right. Everybody look right here. Vital capacity is all of this, right? This is all vital capacity. Okay? Vital capacity, take away the inspiratory capacity. So vital capacity, take away the whole IC, what's left? Huh? Not ERV, what is it? FRC.
FRC and ERV?
No, not FRC and ERV. FRC,
the whole thing.
Yeah. So if I have vital capacity, right? Whole vital capacity, and I take away the inspiratory capacity, then what's left is FRC. The FRC. Boom, boom, boom. That's what's left, right? FRC. FRC. And then finally, TLC, which is all of it. Total lung capacity minus the IRV minus the FRC. All right, so we got total lung capacity, right? TLC, that's all of it. Now let's subtract IRV. All right, so we take away IRV, then we take away FRC. So let me get two pieces of paper. We have TLC. We take away, what is that? IRV, take away the IRV, and then take away the whole FRC. What's left? VT. Tidal volume. That answer is VT. That's why you see how important it is to learn that spirogram. You're going to have to know that spirogram is not going anywhere. You're going to have to be able to tell me, define what each one is, how much each one is, and how to do the addition or subtraction to find one. Okay? Yes. No. Vital capacity, take away the whole inspiratory capacity.
Why wouldn't it be ER?
Why wouldn't it be what? Because you got all of this left. You can't just say ERV. What you want to do about the RV? Yeah, IC, take away, VC, which is all of this part right here. This is the VC in the red. Okay, the whole red box, everything you can do. If you take away the inspiratory capacity, right, then all of this is what's left, which is the FRC. Okay, you see it? FRC? That's what's left. This part right here. This is what's left. RV always going to be there, part of it. RV is part of FRC, right? ERV plus RV is FRC. So FRC is what's left. If I have the whole body capacity and I take away the inspiratory capacity, then FRC is what's left. Okay?
I have a question.
Yes.
Why on the previous one, IC wasn't involved? Because you only took
what?
out the IRV.
What you saying?
You only took out the IRV,
What number are you talking about?
number 5.
Number 5.
So I have a question as far as like the IC. Why wasn't the IC included?
All right. TLC is all of it, right?
Mm-hmm.
Okay, TLC, it says minus IRV. So minus the IRV, okay? Then they want you to take away the FRC. Only thing left is what?
So in the IRV, the IC is included.
IC, what they want you to do is you're overthinking it. What they're telling you to do is take the TLC, which is all of it. If you took away the IRV part, take away the IRV part, take away the FRC, the only thing you have left is VT because IRV is part of IC. So if you take that out, all you have left of IC is by tidal volume. Okay, so if you take IC out and take FRC out, only thing you have left is tidal volume.
Okay.
Okay? That's why you guys have to know how to do this. You got to be able to do that so you can take it away, add it, and that's how you can see it better. Okay? That's how you can see it better. Because the IC is both IRV plus VT. So if I take away the IRV from the IC, then all I have left is the tidal volume right there. Okay? So then that's what's left right there. Then they say not only that, they want you to take away the whole FRC as well. The only thing left, you take the FRC and the IRV, only thing you have left is tidal volume.
Okay, because you can't have one without the other to make it complete.
Yeah. Bottom line is, yeah, IC is
Okay.
IRV plus VT is IC. They telling you to take, they didn't say take out the whole IC. They just said take out the IRV part. If they say take the whole IC out, then you have to do all of that.
So if you're saying IRV, trying to take out the IC already.
Yeah, because that's part of it. IRV plus VT is IC. But if they say take IRV away,
Take IC away too.
yeah, that's the capacity. See, there's volumes and there's capacity. They're two different things. IRV and VT are two volumes that make up the inspiratory capacity. So if I subtract the IRV away from the inspiratory capacity, all I have left is tidal volume. Okay, so I could have stopped right there, but they said some more. Then they said, now take out FRC. So if you want to do it break down, let's do the problem like this. TLC minus the IRV will leave me with what? You can say VT, and then take away the FRC, leaves me the VT. No, don't do it like that, because that might confuse. That might confuse. Let me see. TLV. That would confuse you. TLC is the whole thing. You took away the IRV. So right now you have VT right here, and then they said not only that, but also take out the FRC. So all you got left is what you see. Tidal volume. Okay? Just go by what you see that's left. All right? It's difficult until you practice it and memorize the spirogram. You got to memorize that box, be able to write that box down, right? And to be able to do that, all right? So that way, when you have your test, I won't mind. I'll give you a scrap piece of paper, and you can draw your spirogram, your formulas, whatever you want to draw. Your formulas, your spirograms, you can write all those things down and then take your test. All right. Moving right along. The next thing we got to work on. Let's focus on the 3 volumes and the 3-minute volumes right quick. 3 volumes and 3-minute volumes. Right? You got 3 volumes and you have 3-minute volumes. The 3 volumes are alveolar volume, tidal volume, and dead space volume. Alveolar volume, tidal volume, and dead space volume. Okay? This is the formulas. Alveolar volume is simply tidal volume minus the dead space volume. Okay? The whole tidal volume, you take away the dead space, and that's what's left is the alveolar volume. Tidal volume is simply 3 cc's per pound of ideal body weight. 3 cc's per pound of ideal body weight will give you that person's tidal volume. So if they don't give you the tidal volume, you'll have to figure it out. And then dead space volume, which is the wasted ventilation, right, is 1 cc per pound, like we said yesterday, or just write 150 if they don't give you a weight. If they tell you what is it, if you have to function in or factor in dead space and they don't give you a weight, you do 150. That's the normal, 150 cc's or milliliters, whichever one is, they both the same. So if I say, Mr. Johnson, what is Mr. Johnson's dead space volume? And I don't give you a weight, what you gonna say? 150.
Is it 150?
Yes. If I don't give you a weight, it's 150. If I say Mr. Johnson weighs 200 pounds, what is his dead space volume?
200.
200. It's 1 cc per pound. 1 cc per pound. If he weighs 120, what's his dead space? Huh? I can't hear you.
120.
120. 1 cc per pound. If he weighs 1,000 pounds, what's his dead space volume? 1,000 cc. 1 cc per pound. Okay? Don't make it harder than it is. Now, if I say, what is Mr. Johnson's dead space, but I don't give you a weight, you got to assume 150. There are going to be some normals, guys, that you're going to have to be able to know, because when they have a problem, they give you a problem. They don't always give you all of the factors. You have to assume other values are normal. So they may give you respiratory rate, they may give you height, they may give you his temperature, and then they may say assume all other values are normal. So that means stuff like CO2, bicarb, pH, weight, dead space, all that kind of stuff. You have to know those normals. Otherwise, you won't be able to figure it out. Okay, you got to know it. All right, so don't forget that. Now, what about this one? What if I say Mr. Johnson weighs 120 kilograms? Mr. Johnson weighs 120 kilograms. What is his dead space volume?
$264.
Thank you. 264 cc's. Dead space is 1 cc per pound. I told you he weighs 120 kilograms. You got to convert kilograms to pounds, and then you know your dead space. Okay? What if Mr. Johnson weighs 70 Mr. Johnson weighs 70 kilograms. 70 kilograms. What is his dead space volume? 154 what? cc's or milliliters. Make sure you get in the habit of saying that unit, because you're gonna have all kind of units. You need to make sure you know which unit you're talking about. Okay, 154 cc's or milliliters. Okay. Now, what about tidal volume? To find somebody's tidal volume, we do 3 cc's per pound. 3 cc's per pound. Dead space is 1 cc per pound. Tidal volume is 3 cc's per pound. All right. So if Mr. Johnson weighs 250 pounds, what is his average tidal volume?
750.
750 ml. Good job. 750 milliliters or cc's. Right? All right. What if Mr. Johnson weighs 175 kilograms? What is his tidal volume? 1155. 1,155 milliliters or cc's. All right, now this IBW is ideal body weight. We'll learn that a little bit on down when we figure everything out. But ideal body weight says that at a certain height, you should weigh a certain weight. That's what ideal body weight is. That means at a certain height, you should weigh a certain pounds, right? So that's why they say about 3 cc per ideal body weight, right? So if he's, hold on. Yeah, if Mr. Johnson is 500 pounds, that ain't his ideal body weight, right? So you would do 500 times 3. That's going to be a huge tidal volume, but we wouldn't give him that much tidal volume, all right? We would have to go by ideal body weight. How tall is he? And at the length, because we go by the length of the lungs. Now, how much you weigh? The length. When we do, when we're trying to give somebody a tidal volume on a ventilator, when we're going to set the volume of how much volume we want to give you, then we're going to set it to your ideal body weight, which goes off your height. Okay? And I'll show you the formula for ideal body weight a little later. Okay? But for right now, let's just get the basics. So, this is what I want to know. This is the question I have here. Everybody has that. Here goes the question. Knowing what I just told you, and the work that you worked on last night, if you worked on it, for reinforcement. I gave you some reinforcement last night. All right. We got Mr. Smith. He weighs 85 kilograms, right? Question is, what is his alveolar volume? What is his alveolar volume? Mr. Smith weighs 85 kilograms. What is his alveolar volume? So you have to find out what is the formula for alveolar volume and plug in what you need to plug in. And if you don't know what you need to plug in, you have to know what that formula is to find the number to plug in. Mr. Smith weighs 85 kilograms. What is his average alveolar volume? Just like algebra, just plugging in and solving. Just write your answer down, because I haven't worked it out. So let me work it out too. What is his alveolar volume? All right, I have the answer. If you are online, put your answer in the chat, and I'll come around. For those who are here, I'll look at your answer. Raise your hand when you're ready. What is this alveolar volume? Whoa. Oh, I might get it. Yeah. Okay. You're right. You're right. I had it wrong. Yep. Write your answer in the chat. If you think you have an answer, write your answer in the chat. Let me check my chat box. Kyra, good. But don't forget to put mLs, Kyra. That's milliliters or cc's. What is his alveolar volume? Everybody else ready for me to check? That's why it's very important to put your formulas where you can get to them. All your little formulas have a certain section or a certain page or whatever to write your formulas, so you can go back to them, because you be hunting for formulas. It's hard to find them like that. We're going to get the answer to that, and we'll take a break. About another minute, and I'm going to go ahead and go over it, because it don't take that long. Okay, Gabrielle has an answer. Let me check. Let me see here. Hold on. Wiley, you're right. Gabrielle, you're a little off. Good. That's the formula you guys can get. Eating is dead. Okay. Good. Excellent. Okay. All right, let's look at it before we take a break. All right, guys. I got somebody else on here. Hold on, let me see if Gabby had another answer. Good, Gabby. Excellent. That is correct. All right, the answer is 374 milliliters. This is how you did it. Mr. Smith weighs 85 kilograms. Okay. Alveolar volume is tidal volume VT minus VD. All right, so I just plug in, okay? Well, I know that tidal volume is 3 cc's per pound, right? But I got kilograms, so I have to go ahead and convert. 85 times 2.2 is 187. All right, that's 187. So 187 times 3 to get the tidal volume, right? It's 561. So that's 561 right here, right? Now, dead space. Ms. Taylor, what is the formula to dead space? Dead space volume. Per pound. How many pounds does he work? 187. So 561 minus 187. So alveolar volume equals 374 ml. 561 is the tidal volume. Tidal volume says 3 cc's per pound. How much does he weigh? Times 3. Yes. And you got 561. Yep. So, 85 times 2.2, that converts it to pound. Yeah, to get to tidal volume.
Okay.
Yeah.
That's all I was trying to remember is how to get
Kilograms. Yeah, just always convert your stuff first. If you know you need pounds, go ahead and say 85 kilograms. I know 85 kilograms is 187 pounds. Go ahead and write that so you know that because you're dealing with pounds for all this stuff, right? So if they give you kilograms, go ahead and convert to pounds and use that poundage. All right? All right, we'll for sure do some more of these after break. Come back at 2:05. We're now going to take a break to 2:05. 2:05, we will come back doing some more. I'm going to have another Mr. Smith or another Mr. Johnson. Y'all help me think of some more names. But we will return at 2:05 to continue a few more of these, and then we're going to go over the worksheet I did for reinforcement last night. Starting back, guys, break is over. I now have 2 more problems on the board that we're going to work together, give you some time to work them out, and then we got to go on to the minute ventilations. When we add the frequency, or we multiply the frequency in there to find out how much of this volume we've been learning is moving in and out of the lungs per minute. All right, here we go. Number 1. Number 1, Miss Jackson. Miss Jackson is breathing at a rate of 30 breaths per minute with a tidal volume of 600 mL. What is her dead space volume? Now, when you get a question, guys, be sure to pull out what you need. A lot of questions will add fluff, and it might be a whole bunch of stuff you don't even need. You just pull and pick out of the question what you need to answer your question. Okay, so out of the case study, this is called a case study, right? It's giving you some vitals and some numbers of a patient, and then they start asking you questions. All right, you pull out what you need. If something's up there in the question that you don't even need for your answer, then you just don't use it. All right, pull out what you need. So Miss Jackson is breathing at a rate of 30 breaths per minute. She has a tidal volume of 600 mL. What is her dead space volume? Right, that's number 1. Number 2 says David is 75 kilograms and is has a temperature of 41 degrees Celsius. He's short of breath and he has the chills. Okay? What is his tidal volume? What is his alveolar volume? What is his dead space volume? And then tell me what his temperature is in Fahrenheit. Okay? Pull out what you need. Working on number 1 first. Everybody just do number 1. If you're online, put your answer in the chat. When you're ready for me for number 1, just raise your hand. I'll come look. These are your information, right? All you need. Ready? Dead space volume. Dead space volume. Oh. I didn't say anything. Dead space volume. All you're looking for, all you want to know is what is the dead space volume. So you only pull out what you need from the question to answer the question I'm asking you. What is the dead space volume? Anybody online? If you have anything, let me check my chat. Everybody's getting the same answer. No, Cora? Thank you. You have to tell me. I'm trying. How do you find dead space volume? Tell me what the dead space volume is. 160 per what? Did I give you a weight?
No,
Then what do you do?
150, right?
That's it.
I know it's 150.
That's it. I'm making it harder than it is. Pull out what you need. Anybody else online? All right, so let's look at number one together. Miss Jackson is breathing at a rate of 30 breaths per minute with a tidal volume of 600 mLs. What's her dead space volume? The dead space volume formula is 1 cc per pound. Did I give you a weight? I did not give you a weight.
I have a question. Why wouldn't it divide by 3 since you gave us the tidal volume?
Because I'm not asking for the tidal volume. I'm asking what her dead space volume is. The formula for dead space volume is 1 cc per pound. If I don't give you a weight, you assume 150. What I put on the board, that is your vital information right here. Dead space volume is 1 cc per pound. Okay? If I don't give you a weight, if they don't.
I mean, I get that, but then when you go to the tidal volume, you would have to use that same weight to get the tidal volume, right? So you have to multiply 150 times 3.
No, you're doing too much, Miss Wiley.
Okay.
Just answer the question what they ask you. I asked you, what is her dead space volume? Her dead space volume is 1 cc per pound. You don't know how much she weighs. If you don't know how much she weighs, you can't start taking it from other things to assume her weight. She could be 700 pounds, okay? And just breathing a little bit. You never know. You can't assume like that. What you have to do is, if I don't give you a weight, you have to use 150 because that's the normal that's the normal dead space volume. The normal dead space volume is 150 cc's unless they give you a weight. If they give you a weight, then you do the conversions and you do it like that, okay? Don't overthink it. Just do what they ask, what the question asks. You can't go to the tidal volume and try to deduct dead space away from the tidal volume. That's not what you do. See, all of this was fluff. Her rate at 30, her tidal volume at 600, that was just extra. That was just some fluff, right? You didn't have what you needed to answer that question, so you have to put 150. See, what y'all trying to do is say, well, if our tidal volume is 600, then if you divide, see what you're saying, I divide it by 3, that's going to give me her weight, right? So her weight will be this. You don't do that. You have to go, because people's tidal volume, they could be breathing different than what they should be breathing. You understand? If my tidal volume should be 500, but my tidal volume might be 200. I might have atelectasis, I might have consolidation, I might have a low compliance, right? And I don't have a lot of volume in my lungs. I might have a restriction, right? I may weigh 200 pounds, but I might have kyphoscoliosis. So my tidal volume is not going to reflect what it should be. because of my restriction. So you can't assume like that. You have to go by what they give you. If they don't, to get dead space, you gotta know the weight. If they don't give you the weight, you use what? 150. But that's a good deduction. What you guys tried to do as far as deducting that problem. I see what you're doing, but you can't do that. Say what? All of your formulas right here. On this problem here, I didn't give you a weight. I didn't give you a weight. You have to use 150. All right, number 2. David is 75 kilograms. He has a temp of 41 degrees Celsius. He's short of breath and has the chills. Okay? His tidal volume is what? His alveolar volume is what? And his dead space volume is what? Based on what you are given. And I'm going to show y'all another thing. When we work on that worksheet we have, it tells you what is the tidal volume, but it gives you a tidal volume. You say, well, the weight is different. Which one do I use? You always use what's given. Okay? You always use what's given in the problem. If they don't give it, you have to assume the normal value of that item. Okay? Like CO2. The normal CO2 is 40 millimeters of mercury. Right? So if I ask you a problem that you have to figure in CO2, and I don't give you the CO2, you have to assume it's 40. You can't say, well, he's breathing fast, so it can't be 40, it's probably low. No, you can't do all that. You have to go with what we give. All right, so let me work it out with you. All right, let me check my chat and see if I have any answers. Good, Kara. On the tidal volume, your alveolar volume and your dead space volume are absolutely correct. Now the temperature, I don't know yet because I haven't worked that out. I don't have the formula in my face and I ain't memorized. That's what it is? Okay. Well, if I see everybody with the same one, it's probably right. Here comes Julie. All right, but your answers are right, Kara. Good. Good. 131. It's a little different than what I'm saying. I don't know. I didn't work it out. Yeah. 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 All right, guys. Looking good. Now we're getting the hang of it. Now let me check my chat one more time for those who are online. Yeah, the boy says 41. Miss Wiley, you have an answer for me? Gabrielle, you got an answer for me?
No, not yet.
Okay. Miss Wiley, you still with us?
I'm listening, but I'm on a phone call. I have
Okay, yeah. Yeah, just let me know when y'all step away. That way I don't have to call. I won't call you. All right. So let's look at it. All right. David is 75 kilograms, right? 75 kilograms, and he's febrile at 41 degrees Celsius. So he's febrile. That means fever, right? Afebrile means no fever. So he's febrile, and he has shortness of breath and chills. So what is his tidal volume? Well, first we have to find out what his pounds are. Because tidal volume is 3 cc's per pound. 75 times 2.2 to get pounds is 165 pounds. Okay? 75 kilograms is 165 pounds. So 165 times 3 gives us the tidal volume, which is what? 495? 495 milliliters. All right. And then to find out the alveolar volume, we got to first find out what the dead space volume is. Okay. Well, if he weighs 165 pounds, what is his dead space volume? 165. 165 milliliters. 495 minus 165 is what? 330 mLs. And then 41 degrees Celsius is what? 105.8 degrees Fahrenheit, which is almost dead. Very, very sick. Yeah, plenty of them. All right. That's how we do this, guys. This is how this works. Okay? You have to be able to look at what the question is asking you and be able to utilize those formulas that you learned and use them to what you need. You might not need all of them for that problem. Just pull out what you need and answer the question. Okay? Pull out what you need, answer the question. That problem could have been chalked with that problem could have been chalked with potassium, sodium. I could have asked you what is his sodium, what would be his normal sodium, his white blood count, right? What do you expect to see on his white blood cells since he's febrile, right? Elevated what? If I get a blood on him, what do I expect to see elevated with a fever of 41 degrees Celsius? Huh? Now, well, blood pressure might be up because he's sick, but what blood value am I looking for? What part of his blood, what thing in his blood will be elevated? Which cells? White blood cells. His white blood cells will be elevated. What do you say, alveolar? Yes, because white blood cells are your leukocytes, right? Those are your the ones that fight. Those are your circulate defenses, right? Your white blood cells. So if they're up, you might have a bacterial infection, right? Causing him to have chills and be 41 degrees Celsius. He's 105. That's very high for an adult. Very high. He's very ill. Okay? Breathing 30 times a minute. You'll be able to use that next when we get into the minute ventilation. All right? Now, that is what's next. Minute ventilation. Now, we learned the volumes of the lungs. Now we have to think about the minute ventilation. How much of that very volume is moving in and out in 1 minute? Okay, that gives us a really good picture of his ventilation status, because ventilation is CO2, right? That is respiratory. Are we blowing off too much CO2? Is he not blowing off enough CO2? That's when we look at minute ventilation. So instead of saying, well, his rate is this and his volume is this, we can just look at the minute ventilation, okay? And that'll give us a very good look at how well, if at all, our patient is ventilating, okay? Which is the number one thing we're looking for, ventilation, right? If you're not ventilating, it doesn't matter how much oxygen is in the room. If you're not breathing it in, then you're not using it, right? So ventilation is key. All right, and that is your job as a respiratory therapist. Now let's look at minute ventilation. Huh? That's why you have to practice and you go home practicing. Make up your own problems. Now, when I'm making up these problems, I'm making them up on the fly. Mr. John, I'm thinking of names, and then you just figure them out. Huh? Miss Parker? All right, I'll take you one to Miss Parker. Just don't give me West Kalinsky or nothing like that, and I got to try to spell. All right. Minute ventilation. Here are the values for minute ventilation. Regular minute ventilation is frequency times tidal volume. Okay, you take that tidal volume you found and multiply it by the frequency. And that will be how much volume he's moving in 1 minute. Minute ventilation is frequency times tidal volume. Remember, minute ventilation has the dot in the middle of it. On some worksheets, I can't put the dot, or on online, I can't put the dot. So you have to really know what it's asking. If it's talking about minute ventilation, make sure you're using that formula and not the regular volume. Okay. All right. Alveolar minute ventilation. Alveolar minute ventilation is frequency times tidal volume minus dead space, right? Because that's how we find alveolar volume, right? Tidal volume minus dead space. Now we're just going to multiply by the frequency. So that's alveolar minute ventilation. Mm-hmm. That's the respiratory rate. We follow the problem. Yeah. Mute your mic. Somebody needs to mute their mics.
Thank you, people.
All right. And then dead space minute ventilation, of course, the VD with the dot in the middle, right, is frequency times dead space, or you can say the minute ventilation subtracted from the alveolar ventilation, or you take minute ventilation minus alveolar minute ventilation. So if you find these two, you can subtract this one from this one, and it'll give you this one. Okay? You can subtract this one, alveolar minute ventilation, from the total minute ventilation, and that will give you the dead space minute. Or you can just work it out like this. Either or. It's the exact same. You're just putting frequency in. You're just putting frequency in. Now, the key that I need you guys to understand is when we multiply the frequency to the volume, right? You want to make sure that you put a decimal. You make the volume a decimal, because the answer for minute ventilation is always in what? Liters. The answer for minute ventilation should always be in liters. Okay? So, I should have that. These are the ones we're working on now. Minute ventilations. I'm gonna have to erase so I can do some. I push this out the way so I can use the other board. I'll give you a minute to write these down. And then we're going to start working them. These guys, these are exact same thing as your volumes, except you're factoring in the frequency. The frequency is the respiratory rate. Okay, how fast or slow are they breathing? And that will tell me how much of this volume is being moved in 1 minute. We're going to learn a little breakdown of dead space after this. We'll learn a little dead, because there's 4 types of dead space. And we're going to, it's really simple, but I got to make sure I get you understanding, write that down too. There's 4 types of dead space. All right. Here we go. Now we already know the volumes, right? Now we're going to, this key part right here. Before you multiply the volume, change to a decimal. For instance, minute ventilation is frequency times tidal volume. Use a black ink. Minute ventilation is frequency times tidal volume. Now, once I find whatever volume it is, when I find that volume, I change it to a decimal before I multiply so that my answer comes out in liters. Okay? So for instance, example, if Miss Parker tidal volume is 500 cc, then when I plug that in, I'm going to change to 0.500 or just 0.5 and multiply. That way my answer comes out in liters. Okay? Got that? All right. Now, if you did it in milliliters and you that's how you did it, but the answers are going to be in liters. If you know which one it is, you can still come out right. You don't have to, but that's the way you make the answer come out in, but you're going to have to convert it at the end. So say if you do, well, you're going to end up, yeah, you start off like this and you'll end right. But don't do this too soon. Don't do this to add or subtract. You only do this before you multiply. Before you multiply, you change to a decimal. Don't change to a decimal. For instance, alveolar minute ventilation is tidal volume minus dead space volume. You don't put 0.5 and 0.3 when you get to subtracting. Don't do that. It might still work out mathematically, but I wouldn't do that because it may throw you off. Okay? All right, so for instance, Ms. Parker had a tidal volume of 500 and a respiratory rate of 12. Well, minute ventilation would be 12 times 0.5. Frequency is the respiratory rate. Breathing 12 times a minute at 500 milliliters or 0.5 liters. Yeah. So 12 times 0.5 is what? 6. So the answer is minute ventilation of 6 liters. If not, you would have got 6,000 and you would have had to say that's 6 liters. Right? Huh? Yeah, that dot means minute ventilation. Okay. Yeah. But see, a lot of times when I'm writing or Microsoft doesn't, Word don't have a way to put the dot there. Right. So you have to make sure you. I can see dot. Yeah. That dot signifies your minute ventilation. Now we're dealing with the minutes. Okay? Now we're dealing with the minutes. All right, so let's look at it. Or you multiply, change to a decimal. Okay. All right, so let's say for instance, Mr. Parker is short of breath, 37 degrees Celsius, has a 180/95 blood pressure, right? He has a respiratory rate of 25 and weighs 60 kg. My question, what is Mr. Parker's minute ventilation and what is Mr. Parker's alveolar minute ventilation? That's all I want to know. Some other things you're going to have to find out to find that, but all I want to know is those two things. So this is the question, guys. Mr. Parker, he came in the ED. He presented to the ED, very short of breath. He has a 37 degrees Celsius temperature. He's hypertensive at 180/95 millimeters of mercury. His respiratory rate is 25 and he weighs 60 kilograms. What is his minute ventilation? What is his alveolar minute ventilation? Those are the formulas there. Use some time to work those out. Those of you online, you can put the answer in the chat. All right, let's see. Ready? Good. All right, now you're 392, right? If you want. Yo. All right. Anybody online? Let me check my online before I go over it. Oh, nobody answered online. Okay. All right, here we go. Now, Mr. Parker is short of breath. All that. What I want to know is minute ventilation. Minute ventilation is frequency times tidal volume. All right. So in this case, I'm gonna have to find out what his tidal volume is because it's not given. Right. So how do I find tidal volume? 3 times the pounds. Right. 1 cc per pound. 3 c. I'm sorry. 3 cc's per pound is tidal volume. So first thing I gotta do is convert 60 kilograms to pounds. So this is 132 pounds, right? 60 kilograms is 132 pounds, right? Now we can work, all right? So tidal volume is 3 cc's per pound. So 132 times 3 is what? 396. So that would be 0.396. I'll just show where everybody can see it. So we found out that the tidal volume is 396 mLs. Okay, that's the tidal volume. So I got to plug that in here. So frequency is the respiratory rate. He's breathing 25 times a minute. 25 times. Remember, when you're about to multiply, you change this to a decimal before you multiply because your answer should come out in liters. So if his tidal volume is 396 mLs, that is 0.396. 25 times 0.396 gives me a minute ventilation of 9.9 liters. 9.9 liters. Okay? Now, the next thing I asked, what is this alveolar minute ventilation? This alveolar minute ventilation. Well, the formula for alveolar minute ventilation is frequency times tidal volume minus the dead space volume. Right? We already know that the tidal volume is 396, so that would be F 396 minus, what is his dead space volume? 132, because dead space is 1 cc per pound. 60 kilograms is 132 pounds, so that would be 132 cc's of dead space. 132. All right, don't change decimals until you're ready to multiply. Okay, so 396 minus 132 came out to be what? How much? 264. 264. Now I can change that to a decimal. Make it 0.264 times the frequency of 25. Right? And that gives me an alveolar minute ventilation of 6.6 liters. That's how much is going in. So look at this one right here. Totally, there are 9.9 liters of gas going in and out of his lungs every minute. But only 6.6 liters of that is taking place in gas exchange, right? Where the magic happens. The magic happens in the alveoli, right? The magic happens in the alveoli. So out of that whole 9.9 liters that's moving in and out of Mr. Parker's lungs, only 6.6 liters of that is actually taking place in gas exchange. So that leaves some wasted ventilation, which is then called dead space minute ventilation. When you just subtract it, 9.9 minus 6.6 is what? 3.3 liters of dead space ventilation. That means 3.3 liters is wasted. It's wasted, right? 9.9 liters is total. Mr. Parker, in this problem, has a total of 9.9 liters of gas moving in and out of his lungs every minute, correct? Correct, Ms. Judy? Good? 9.9, right? But the magic don't happen until you down in the what? Alveoli. The alveoli is where gas exchanges, where the CO2 comes into the alveoli and oxygen leaves the alveoli to the bloodstream. That's the gas exchange. That's the magic down in the respiratory bronchioles, also known as the parenchyma of the lung, right? That's the magic. So all the rest of that gas is called wasted ventilation, which is dead space. Dead space ventilation, AKA wasted ventilation, okay? So we're gonna find out next, what are the types of wasted minute ventilation, or types of dead space, right? There's different types of dead space, which is what we're gonna talk about now. So let's take a break, come back at 3 o'clock. Where the trash can go? Oh. All right, let me recap that. We've learned volumes, and then we've learned minute ventilation, okay? You have the formulas for both. Now, this last problem, we did the minute ventilation for Mr. Parker, right? Which was frequency times tidal volume. We found his tidal volume by using the tidal volume formula and found out that he is moving 9.9 liters of gas in and out of his lungs every minute. But out of that 9.9, only 6.6 of those liters are actually taking place in gas exchange, right? That's the only amount that's really doing the work. So the rest of that, which is 3.3, because you just subtracted 2, the rest of that is just wasted minute ventilation, just wasted. It's wasted, right? It's in the conducting airways, wasted. That's called dead space minute ventilation. That's the gas that is wasted every minute for this person, okay? So we are going to take a break. It is 2:50. We're going to take a break till 3 o'clock. I'm going to stop the recording, and we will come back at 3 o'clock and talk about the types of dead space. All right, we are back from break. Before break, we did a few of the volumes and some of the minute ventilations, learning the difference between the two. You would definitely need to practice those formulas and do as many as you can for your reinforcement. We will now go on to the dead space a little bit more in depth. Dead space is that wasted ventilation that doesn't take place in gas exchange. Remember that all of the airway that is conducting, right? The conducting zones. The conducting zones are wasted, right? The only gas that matters is the gas that makes it to the alveoli. That is where the magic happens, right? That's where the magic happens. Gas exchange, right? That's when we're actually doing external ventilation or external respiration is at the alveoli level, okay? Now, from the nose all the way down to the terminal bronchioles are just conducting zones. They have passageways that lead the air or deliver the air to the parenchyma or the alveoli where the gas can exchange, right? Now, but there's types of wasted ventilation or dead space ventilation. From the nose down to the terminal bronchioles is called anatomical dead space. That's the first one. The first types, we have 4 types of dead space. The first type is called anatomical. It's just anatomically, right? Just the, because you're a human, you have anatomical dead space, and that is the space or the area from the nose all the way down to the terminal bronchioles. That is called anatomical dead space. Anatomical dead space. All right. So I'm going to share my screen that shows it a little bit better so you can take these notes that talk about the dead space. All right. Here we go. VD is dead space. We've already learned so much about it, how to get it. It's the part of the minute ventilation is wasted, does not reach the alveoli where external respiration occurs. So any of the gas that does not make it to the alveoli is dead space. Okay, it's dead space. It is not participating in gas exchange, not participating in the magic, right? 4 types. Anatomical is VDNAT. I put that on the board the other day. But VDANAT, right? That's how you abbreviate it. That will be the dead space that's in the anatomical section of the lungs, right? What does it say? Fills the space in the conductive airway. The gas that fills the space in the conductive airways is anatomical dead space, right? Because from the nose to the terminal bronchioles, that's the conductive airways. All right, if you get a question to ask you, what is this part in the conductive airways or not? If it's not the respiratory bronchioles, then it's, yes, it's conductive. All right, only thing that is in the parenchyma or the gas exchange part will be the respiratory bronchioles, right? That is called the parenchyma of the lung, right? That's where gas exchange takes place. I can't say that enough. So, 4 types of wasted ventilation, which is dead space. Number 1 is anatomical. Fills the space in the conductive airways. The next one would be alveolar. Oh, it's possible for our alveoli to have some wasted ventilation? Yes. Some alveoli are not perfused, right? If you have an alveoli that is open, but there's no blood flow to it, then that gas that's in there is being wasted, right? It's not any gas exchange taking place because you have to have blood and you have to have volume for gas exchange to take place, right? You have to have the alveoli and you have to have the capillary around the alveoli, okay? So what if you have an open alveoli but no blood to pick up the oxygen? It's wasted, okay? That will be wasted. So alveolar dead space is alveoli that are not what? Perfused. Perfused means have blood flow. Perfusion means blood flow, right? So alveoli that don't have perfusion are open up alveoli, wide open, but no blood to pick it up. That is called wasted. That's also wasted. Might as well have been in the conductor because there's no capillary picking it up, right? So that is alveolar dead space. Number C, physiologic. VD-PHYS, that's physiologic dead space. It's just adding the 2. Anatomical plus the alveoli together is physiologic dead space. Physiologic dead space is adding the 2 together. Anatomical and alveolar. Then you have mechanical, right? Mechanical dead space. That is when you add dead space to somebody, right? So not only think of somebody that's on a ventilator, okay? Think of somebody that's on a ventilator. Matter of fact, I'm gonna stop my screen there so we can peruse this information a little bit better. All right? Think of somebody that's on a breathing machine. Okay, I'll just say that because you haven't learned ventilators yet. But someone who's on a ventilator, okay, and he has tubing from the machine to him, right? Okay, let's look at it. Let me pull this up so I can share my screen on some images. All right, let's look at this right here. So let me share my screen. All right, take a look at this. This lady here has an ET tube, endotracheal tube, that we said is placed in through the vocal cords, right? It goes through the vocal cords, and that hole that's between the vocal cords is called the glottis. We go into the airway like that, right? That's what that tube is. We put a balloon on the end of it, fill it up so it seals the airway, and we put them on a ventilator. All right, so everybody look at my mouse, right? Now, we already said that anatomical dead space is from right here, the nose, all the way down to her terminal bronchioles, right? That will be her anatomical dead space. And then if she has some alveoli that are open but not getting blood flow, that will be alveolar dead space, correct? Sir. What's that? No, go ahead. Hold on one second. Oh, okay, yeah. His birthday? Mike who? told me that. Where you going? I'm working at the hospital. Oh, wow.
2 more days, 3 more. Friday.
Wow. We're going to do 220. You? Doing everything. Yes, sir.
Thank you.
All right, thank you.
Sorry to interrupt.
Yeah, I didn't know. I didn't know. Was it an email? I didn't. If you see it, forward it to me. If you see it.
No, I was in the meeting. Were you in the meeting?
Yeah. I don't know. I'll talk to you about it. All right. All right, guys. So again, the anatomical dead space is from the nose down to the conductive airway, right? That's anatomically your body is your anatomical, right? Just by sheer location of it. It's not in the inside the lungs, right? Or it's not in the alveoli, so it's anatomical wasted gas, right? All right. Well, if you have some alveoli that are not perfused, right? They're wide open and got a whole bunch of air, but there's no blood around it to take it, so it's wasted. It's wasted, right? Now that would be an alveolar dead space, and when you add those two together, that's what? Physiologic dead space. Well, this is the last one, mechanical dead space. All of this. Now look where my mouse is. All this extra tubing. The gas that's inside this tube, is it gas exchange? Any gas exchange happening inside this tube? No. So all of this is also dead space. So this is what's called mechanical dead space. Anytime I add more dead space to the patient, that's mechanical dead space. So all of the tubing would be mechanical dead space. That's what we call mechanical dead space. When we add tubing, more tubing to your patient, to that breathing circuit, right? That's a completely closed circuit from the machine all the way down to the lungs. That gas is going from the machine into the lungs. So you have anatomical, you have some of the alveoli that are not perfused, that will be alveolar dead space, and then you have extra tubing on the circuit. This right here, this tubing is called mechanical dead space because the oxygen and the gas that's inside of this tube right here is not participating in gas exchange at that moment. It's not in the alveoli, so it's wasted. Okay, it's simple. Okay, make it simple. That's all it is. Anatomical, alveolar, add them two together. That's physiologic, and then added tubing would be mechanical. All right. All right. Let's go back to the notes. Well, let me let you see what I'm talking about as far as the alveoli, so we understand alveolar dead space. Okay. Look right here. Alveolar dead space. All right, so if you have an alveoli, right? We have a good old alveoli, right? Full of oxygen, wide open, but there is no blood around it. So let's just say, like if this was the blood flow, it'd be like spotty, right? Just barely any perfusion, right? There's no blood picking up the oxygen out of the alveoli. So that gas inside of the alveoli is wasted. That's called alveolar dead space. Because it's wasted. Okay? So write this down on somewhere where you make sure you know, because you're going to have to know the difference between dead space and shunt. Okay? Dead space is this. Ventilation with little or no perfusion is called dead space. You have a dead space situation when you have ventilation without or in excess of perfusion. Let's say that might sound better. You may see that better. Ventilation without or in excess of perfusion. That is called dead space. Ventilation without or in excess of perfusion is called dead space. Okay? So that means it might be a little blood there, but it's way more ventilation than it is blood. That's dead space. Okay? It's being wasted. All right? It's being wasted. All right. All right. We already learned that dead space is normally 1 cc per pound, or approximately how much? Huh? 150 cc's. That's the volume that's being rebreathed pretty much. Because look, when you take a deep breath in and you stop and you hold it, you got air in your conducting zone, right? That's in there. It's not empty. It's not participating, no gas. Only the gas that's changing is what's in the alveoli, right? Only thing that's in the alveoli. All right, alveolar ventilation. See how we couldn't that look at there. Everybody look right here. See how I could not put that dot in the V. Okay, I could not put the dot in the V right here because with the Microsoft Word you just can't put a dot. So alveolar ventilation is this. Alveolar ventilation is tidal volume minus dead space times frequency. So don't get confused about alveolar volume. Are they asking me for alveolar volume or are they asking me for alveolar ventilation? Right? They're going to tell you ventilation. They'll know when they give you that. If they say ventilation, that's what they're talking about because it's supposed to have a dot in the middle, but sometimes you can't put that dot. Okay, if you're not sure, just ask. But if they just say alveolar volume, that's just the volume. Alveolar ventilation should be that minute ventilation formula. Okay, so alveolar minute ventilation is tidal volume minus the dead space times the frequency, which frequency is respiratory rate. Okay. All right, which we've done all those things. Took a lot of time to knock some of that out. All right, terms relating to the dead space. Well, you have normal ventilation. Normal ventilation is adequate ventilation to meet all metabolic needs. Normal ventilation is adequate ventilation to meet all metabolic needs. Now, why do I say metabolic? Well, what is the byproduct of metabolism? What is the waste product of metabolism? Huh? CO2? CO2. So, my body is metabolizing. I got to get rid of that CO2, right? So my lungs' job is to get rid of that CO2 so that I can keep doing my thing. Because if it starts to build up, then my CO2 starts to build up, and that's when I go into respiratory failure. Respiratory failure is when they cannot get the CO2 off, and it just keeps climbing and climbing, and they become acidic because CO2 is a acid, right? It is an acid. So as if I don't get it off of me, then it's going to start building up, and it could lead to respiratory failure. So they say normal ventilation should be good enough for me breathing in and out to get rid of that CO2, which meets my metabolic need. I have a metabolic need to get that off of me so I can keep on burning oxygen and carbohydrates and producing CO2. I got to get that CO2 out of here so that I can keep on doing what I'm doing, right? So normal ventilation is being able to ventilate good enough to meet all metabolic needs. All right, hypoventilation. Remember hypo. Hypo is decreased alveolar ventilation, right? If I'm hypo is always low, right? Less, hypo. Hypoventilation is a decreased alveolar ventilation, minute ventilation, right? Because what all that matters, which minute ventilation is most important? Regular minute ventilation or alveolar minute ventilation? Say it loud, I can't hear you. Which one is more important, minute ventilation or alveolar minute ventilation? Alveolar, because that's where the what? Gas exchange is happening, right? Y'all can't be scared to say it. Just say it. And don't be worried about your answer. It's probably right. Your alveolar minute ventilation is more important because that's where the gas exchange is. I could care less how much dead space you got, because somebody who's 7 foot tall is going to have more dead space than somebody who's 5 foot tall, right? Because of the length of the trachea. It's going to be much longer, right? Anatomically, right? But what's in that alveoli is the same, right? That's what matters. But that's where the gas is, the magic is happening. All right. So if I'm hypoventilating, then I have a decreased alveolar ventilation. That means my alveoli is not picking up that CO2 and getting it out of here. Right. That ventilation is low. So I'm building up CO2. If I hypoventilate, then I am hypercapnic. Remember that? Hypoventilation will lead to hypercapnia. Okay. Now, B says it can be caused by increased dead space or a decreased tidal volume, either one. So look at me. If I'm breathing normal, right, then I should have a normal ventilation. But if I start slow my breathing down and I just take in a little shallow breath, I'm just taking in little bitty breaths, right, then all of my stuff is going to go down. My alveolar ventilation is going to go down. My regular ventilation is going to go down because I'm not taking in any volume, right? I'm not breathing normal. I'm just barely breathing, right? So that can cause hypoventilation. Okay, that's what they're saying. Hypoventilation can be caused by increasing the dead space, or if I just decrease the amount of volume that I'm taking in. Okay. Now, what do we know? We said ventilation is AKA what? What gas? CO2. Ventilation, AKA CO2, AKA acid, AKA respiratory, right? AKA capnia. They're all the same. Okay? And this is the first part that you get a number to go with your ventilation status. Ventilation less than necessary to meet metabolic demands is signified by a CO2 that is higher than 45. Okay? Higher than 45 millimeters of mercury in arterial blood. That's how you know if the person is hypoventilating, because their CO2 is higher than it should be. All right, so on the side, I want you to write down what the value is for CO2. CO2, normal value. CO2's normal value, which is P, partial pressure, right, of arterial CO2. The normal value is 35 to 45 millimeters of mercury. All right? That's the normal value for CO2. If I hypoventilate, then I'm going to have a higher CO2 because I'm not getting it off. If I hypoventilate, means I'm breathing low and slow and shallow, right? So I'm building up what? CO2. And it's going to creep up higher than 45. Once it's higher than 45, that's considered to be hypoventilating. Yes. Pressure. Pressure is the partial pressure. Remember, that was in our first lesson. P stands for what? Pressure. So that right there is partial pressure. What's little a stand for? Big A is alveoli. Little a was what? Huh? I can't hear you. No, I'm talking about the little a. Yeah, little a. Big A is alveolar. Little a is arterial. Gotta know that. Gotta go back. That's why I say go back to 210A. Look at all your little abbreviations. You gotta study that stuff. You can't forget to go back because we're building on those things. And if you totally forget that, you're gonna be lost. All right. P stands for pressure or partial pressure. Little a stands for artery. And CO2 is for carbon dioxide. So the pressure of carbon dioxide in the artery, that's what that means. What? Pressure. The pressure of CO2 in the artery. The pressure of CO2 in the artery. It's in your notes in 210A. P is for partial pressure. So the partial pressure of arterial CO2 is what PaCO2 stands for, okay? All right. So if I'm not blowing off enough CO2, then my PaCO2 is going to go up. The number's going to go up. The normal value is 35 to 45 millimeters of mercury. You're going to need to know that, but you'll learn it more when we get into arterial blood gases, because there's more things in the blood gas than just CO2. Okay? Let's go back. All right. Let's look at hyperventilation. If somebody is hyperventilating, they breathe in what? I'm saying if they're hyperventilating, that means they're breathing what? Fast. Yeah, fast or too much, right? Breathing too fast or breathing off too much CO2. So hyperventilation causes an increased alveolar ventilation. We don't want the ventilation to be high either. We don't want it to be too low. We don't want it to be too high. We want it to be just right to keep the CO2 between 35 and 45. Okay? If the CO2 start, what happens if somebody hyperventilates? If somebody was to panic in this room and start hyperventilating, what's going to happen eventually? They're going to pass out because they blowed off too much CO2. So the CO2 is vital. It needs to be right smack dab in that range. Too little will pass you out, and too much will make you pass out too into failure. Okay, that means you ain't breathing at all. You stop breathing, your CO2 gonna start building, and that's going into respiratory failure. Okay, so it's got to be just right, and you're gonna learn how to find out what it is by sticking them in their artery and getting these values that you're gonna get, and find out, okay, what do I need to do? Do I need to make adjustments on the ventilator? What adjustments do I need to make? How much to make it? Right, by looking at that blood. Right, respiratory therapy. Okay, real respiratory therapy. Now, so if they're hyperventilating, they're breathing really fast, right, or blowing off too much CO2. That causes an increase in alveolar ventilation, which means you blow off more CO2. Okay, it can be caused by a decrease in dead space or an increase in your tidal volume. Main thing is ventilation more than necessary to meet your demand. You're blowing off too much, right? It's signified by a PCO2 or PaCO2 less than 35, right? So CO2 is an acid, it is respiratory, and its range is 35 to 45. If it starts to creep up above 45, that means you ain't blowing off enough. If it starts to go lower than 35, then that means you're blowing off too much, right? We want it to stay in the middle. The absolute normal for CO2 will be 40 millimeters of mercury. That is the absolute normal. So if somebody asks you, what is the normal value for CO2, smack dab in the middle would be 40. 35 to 45, what's in the middle? 40. Okay, so if it's less than 35, they're breathing off too much. If it's more than 45, they're not breathing off enough. Okay? Now you can see why COPDers, what kind of CO2 number would a COPDer have? Think about that. What kind of CO2 number? Greater than 45 or less than 35 for a COPDer? Think, okay. You say greater, you say greater. Anybody say anything different? Anybody online say anything different? A COPDer, what type of CO2 do I expect them to have when I look at their numbers? Would it be greater than 45 or less than 35? What you think, Judith? for a COPD. First, think about what a COPD is. What problem do they have? I can't hear you. Low, okay. So a COPD is an obstructive. They can't get the air what? Out. COPDers can't get the air out. So we breathe out what? Carbon dioxide. So if they can't get the air out, they building up what? Carbon dioxide. So their numbers will be greater than 45 because they retain it. They retain CO2 because they can't get it out, right? When they exhale, they don't get all of their CO2 out like we do. So it builds up. And so when we look at an ABG and we look at their CO2, we expect their CO2 or PaCO2 to be higher than 45, higher than normal, because they're building it up. They can't get it out. Okay? That's how you have to be able to make these distinctions, guys. You got to be able to link the disease with the values, right? Oh, okay, yeah. So you said COPDers can't get the air out, and when we exhale CO2. So that means his FRC gonna be higher, right? His total lung capacities are higher because he can't get it out. And not only that, since we blow out CO2 and he can't blow it out like I can, his CO2 gonna be higher than mine, right? And high is greater than 45. Anything greater than 45 is high, okay? Anything less than 35 is low. That's the range. That's how you have to be able to put this together. Okay? All right, ventilation and perfusion. Ventilation and perfusion. This will be the last one we do for today, the last lesson, lesson 4. And we're gonna do lesson 5. We'll do lesson 5 on tomorrow, which is shunting and dead space. And that'll be it. All right. So lesson 4, ventilation and perfusion. All right. This is where you got to really stay focused. Okay. Let's look at this same alveoli again. Ventilation to perfusion is known as the VQ ratio. VQ ratio is V for ventilation and Q is for perfusion. I don't know why, but it is. Perfusion. Ventilation is the gas. Perfusion is the what? Ventilation is the gas. Perfusion means what? Blood. Perfusion is the blood. Perfuse means blood flow. Okay? Stop the screen share so those online can see what I'm doing on the board. All right, ventilation, VQ ratio is ventilation to perfusion, VQ, okay? It should be 4 to 5, okay? And what I'm getting is 4 liters of alveolar ventilation to 5 liters of cardiac output. So VQ ratio should be 4 liters per minute of alveolar minute ventilation to 5 liters per minute of cardiac output. That's normal, 4 to 5. Cardiac output. It's heart, right? Everybody look up here. This is the heart, right? The systemic. What side is the systemic side? The left side, right? That's the side that goes to the body. Well, that left ventricle strokes out 5 liters per minute of blood. Okay, that's called cardiac output. How much is your heart putting out? That's what they measure. How much blood is coming out of that aorta every minute? 5 liters of blood per minute comes out of your heart. You know how to, you seen a 2 liter, right? A 2 liter of drink? Yeah, the big, right? 2 liter. Not this. But the regular Sprite, yeah. That's 2 liters. So 2 of them and a half, that's the amount of blood your heart puts out every minute. 5 liters. 5 liters is your cardiac output. That left side of that heart, that left ventricle, has to be able to put out 5 liters per minute to keep up with your metabolic demand. That's normal. 5 liters per minute. That's cardiac output. That's a lot of blood, right? That's a lot of blood, but that's what your heart is doing. Okay? Now, it should match up with the amount of gas that's coming out of each alveoli. So each alveoli, they say it should be around 4 liters per minute for alveolar minute ventilation, right? When we did minute ventilation and all that, if the alveolar should be putting out 4 liters to that 5 liters of cardiac output. That is ventilation to perfusion ratio. It's kind of like comparing ventilation to perfusion. They should be fairly close, 4 to 5, right? They should be fairly close. If I have, so this is how we find out where we have a problem, when we have what's called a VQ mismatch. It ain't matching like it should, right? So if I had already told you that if I have volume but no blood, that's called what? I just told you that having volume in excess of perfusion is called what? Volume in excess of volume without or in excess of perfusion is called what? Dead space. Dead space. Because it's wasted, right? You got this nice, big old, pretty alveoli full of oxygen, but there isn't any blood around it? No. So if you have gas and no perfusion, that is dead space. Okay? You want to learn next, if I have perfusion and no gas, that's called shunt. Right? Remember when I told you that sometimes the blood goes from the right side of the heart to the left side without picking up oxygen, and that's called a shunt? Well, this is why. The blood came, the blood came, right? Let's just say, let's look over here. We had a nice little blood flow came, right? All right, so say we had a nice little blood flow was coming, right, to the alveoli, right? We got the blood, but look at my alveoli. Look at that alveoli. It's closed, right? It's closed. So I got plenty of blood, but did it pick up any oxygen? It's going back to the heart without picking up that oxygen. That's a right to left shunt. So that stands to reason that if I have an alveoli, if I have no, so this is the term. So write this down. Because I already told you the dead space. Let's do it again. Say it together. Oh, you ain't got to say it, but write it down. Ventilation without or in excess of perfusion is dead space, like Judith told us. Okay? I'm gonna write it down. All right. Ventilation without or in excess of perfusion equals dead space. That equals dead space. All right, now here's the other way. Perfusion without or in excess of ventilation equals shunt. Make sure you got that wrote down. You understand what I'm talking about, because we talked about right to left shunt. You understood, but now you can really see, because the blood came from the right side of the heart and then went to the lungs, but the alveoli was closed. The blood was there, but the alveoli was closed. So it returned to the heart unoxygenated. That's a shunt. Perfusion was there, but no ventilation because the alveoli was closed. If it's closed, ain't no ventilation, right? So it came to the store to pick up some goods, but the store was closed. So it returned home with the same money, but it couldn't buy it. Okay? Couldn't go pick it up. Right? Say you need batteries, right? You need batteries for something. Very important. You go to the store to pick up the batteries. The store is closed. So you return home without the what? Without the batteries. Because the store was closed. So when the blood goes to the heart, the lungs to pick up oxygen, but if the alveoli closed, it's going to go back to the heart unoxygenated. That's a shunt. Okay? That's a shunt. All right? So this right here will be a shunt. Right? As a matter of fact, let me make it blue. So it'll be unoxygenated, right? So blood came from the right side of the heart and touched the alveoli, but the alveoli was closed, so it came back the other side, deoxygenated, right? No O2, no O2 from the right to the left. Right? That's a shunt unit. How to shunt. But if we have this, alveoli nice and open, and but we don't have the blood flow. We got an open alveoli, but the, let's just say, blood flow is just barely, right? Ventilation without or in excess of perfusion, this is called a what? Ventilation with no perfusion is called dead space. That's ventilation but no perfusion. Over here you have perfusion but no ventilation. Okay? And when you have perfusion, you got the blood, but it goes to the lungs. Alveoli closed, it goes back to the heart, deoxygenated. Didn't pick up the oxygen. That's a right to left shunt. Okay? That's very important. Very important. So I hope you guys understand that. That's the difference between a shunt and dead space. All right. So this, let's just go ahead and say this is a shunt unit. Unit in the alveoli. This is a dead space unit, right? And then this one here, let's look at this one. Wide open, right? And then we have the oxygenated blood comes in, And then oxygenated blood leaves. Right? That's a normal unit. Ventilation, no perfusion, right here. Ventilation, no perfusion is dead space. VD is dead space. Because it's wasted. That's ventilation there, but it's being wasted. Remember, dead space is wasted ventilation. So if I got my alveoli wide open, but there's no blood to pick it up, that's wasted. Right? Dead space. This one here is called a normal unit. This would be a normal unit with about a VQ. This would be a VQ of 4 to 5. Normal, right? Good volume, good ventilation and good blood flow. That's what we want. So tell me how this one would look. How would, talking about ventilation to perfusion right now. If we said the normal unit, we said ventilation is 4 to 5, right? VQ should be 4 liters of alveolar volume to 5 liters of cardiac output. Okay? So this is a normal unit right here. Blue blood over here, it gets oxygenated, wide open, goes to the heart, oxygenated. This is normal, a normal unit. We should have a VQ ratio of about 4 to 5. 4 liters of alveolar volume to 5 liters of cardiac output, right? All right. Tell me what it would look like right here. What would, just give me some numbers, what you think the VQ will be for this one. VQ here. So what's going on? So what would it look like? Just give me some numbers that you think it would probably be. This one right here. 4 to 1. That sounds good. Or 2 or whatever, right? But we got ventilation, right? But we don't have the perfusion. V is ventilation, Q is perfusion. Now don't write this 4 to 1 down because that don't mean, oh, that means 4 to 1. That don't mean we're just throwing some numbers out. You would never know exactly. But we're just trying to get the concept. Okay? Showing you that in a dead space unit, we have ventilation. So we got the 4, right? But we don't have any blood. So about 4 to 1 or 4 to 2, right? That's ventilation in excess or without perfusion. Dead space. Okay? What about this one? This table, tell me what you think this VQ would probably be.
So it would be a probably ventilation, right?
Just give me some numbers. Ventilation is for the top. The ventilation, what's going on right here?
It's not open. It's not open.
I'm not open, so it's going to be a low ventilation, right? Okay, you can say 2 to what? 5. Okay, you can say 2 to 5. That will be a shunt because we have we could possibly have 2 liters of alveolar ventilation and 5 liters of cardiac output. And shunt is perfusion without or in excess of ventilation.
So basically, like the shunt is when ventilation is out and perfusion is right.
Yeah, perfusion is there. Perfusion is there, but but for a shunt, perfusion is there, but the alveoli, the ventilation is not there.
Right, and then dead space, the ventilation is there, perfusion is not.
Yes.
Or it's little to none.
Yes, that's it. That's all it is. Right? Normal unit will have a 4 to 5, because normal is 4 to 5, right? Open and it's got blood. What is this one? The last one, which we're going to come to talk tomorrow, but I'm going ahead and show you, take pictures over there, I'm going to stop. But this is the last unit here. So we have 0 and 0, right? No ventilation, no perfusion. That's called a silent.
What? We got quiet.
It's called a silent unit.
Okay.
It's a silent unit.
I ain't heard that.
All right.
That.
Silent unit. The VQ of about 0 to 0. Right? No ventilation, no perfusion is a solid unit. Ain't nothing going on. It's quiet. Okay? Solid. Now that could be, you got 400 to 600 million alveoli. That's just one alveoli, right? You can have a section of your lungs that's experiencing shunt. You can have a section of the lungs experiencing dead space. Those are different disease processes. We look at x-rays, we look at blood work to find that out. We go and do therapy to pop them open or to make the blood flow, right? We do all of that, okay? All right, so ventilation perfusion is where we are, okay? Ventilation to perfusion. Let me share my screen back for the rest of this little lesson for today. All right. So ventilation, perfusion. Ventilation is alveolar ventilation. Perfusion is blood flow to the tissues. VQ is what it's called, and it's 4 to 5. But let's keep on looking. External respiration. We already learned that external respiration is gas exchange between the alveoli and the capillaries, right? The lungs. The alveoli are in the lungs. The lungs' number one purpose is external respiration. Okay? What happens in that external respiration? Carbon dioxide leaves the blood and oxygen enters the blood. That's gas exchange, right? We can say that 1,000,000 times, right? That deoxygenated blood returns to the heart via the superior and inferior what? Vena cava, right? Full of CO2 and a little bit of oxygen, right? And what happens is, this is what happens. But what I tell you that it's all about what? I say gas, move, volume, all that stuff move, blood and volume move to the, it's all about the what? From area of what to what? What did I say? Area of high pressure to what? Low pressure. All right? So what's happening is this. We have an alveoli. All right? And let's just say the oxygen, O2, is about 100 millimeters of mercury. Okay? That's the pressure. Millimeter of mercury is pressure. Inside that, you're going to find that out when we do alveolar equation later, that the pressure of oxygen inside the alveoli is about 100. Okay? Then you have your capillaries over here. Color. All right? You got your capillary. Then you have the oxygenated side. All right? So what's happening? Okay. Well, this capillary, this is full of deoxygenated blood, right? This is the right side, right? What it is the right side has CO2 is about matter of fact, what did you say? CO2 is about, look, pay attention. The CO2 inside of the alveoli is about 40 millimeters of mercury. Okay? About 40 millimeters of mercury. That's the normal CO2, right? 40 millimeters of mercury. Okay? Now, the oxygen inside the capillary, O2 inside of the capillary on the deoxygenated side is about, I think it's about 25 millimeters of mercury. All right? Now, tell me this. This is the physics we talked about. If the oxygen is 100 in here and only 25 in the capillary on this side, what it's going to do?
It's going to the left.
It's going to the left. So that's why oxygen shoots into the capillary. Okay? That's why oxygen goes into the capillary, because the oxygen pressure in the alveoli is 100, but in the capillary it's only like 25. So it goes from high pressure. So, oh, okay, let's go over there. So the oxygen is going to go from inside here into the capillary, right? Now the CO2. The CO2 inside of here is like 0.228 inside of here, but it's 40 out there. So which way is the CO2 going to go? Into the alveoli to be due to so what can happen? No, so you can blow it out. We exhale what? CO2. So that's what's happening, guys. On the capillary, the pressure. It's all about pressure, right? It's all about pressure. The CO2 is about 40 in the capillary, and the oxygen is about 25 in the capillary. Inside the alveoli, the oxygen is about 100, and the CO2 is about 0.228. So that means you're going to go from high to low. So the oxygen is going to go into the capillary, and the CO2 is going to go into the alveoli. That's why you do what you do. Okay? That's the pressure. All about pressure. They go from high to low. So that's what's happening at the alveolar level. That's why gas exchanges from capillary into alveoli, because of the pressure difference. Okay? That is in your book. It's got a good picture of it, explains it. My numbers might be a little off. Okay? My numbers might be a little off, but you get the picture. Okay? Make sure you look when you do your reading, because this is very important. Very important of how that gas moves from the capillary membrane into the alveoli. And this gas is happening because of pressure, but what cell in the alveoli allows for this to happen? Allows for that pressure to even make a difference. Which cell in the alveoli lets the CO2 in and the O2 out? Type 1. So you got to know that, right? It all starts to build together. All right? All right. So, external respiration. Now, carbon dioxide leaves the blood, oxygen enters the blood because of pressure, because of the pressure difference. Okay? Because of the pressure difference. Look in your Egan's book so that you can really look a good picture of gas exchange. Matter of fact, did I write it down? Page 250 in the new book. You can just write that down. You ain't got to look right now, but page 250 in the new book kind of talks about that pressure difference, right? It shows a little bit of difference of pressures, right? Make sure you're doing your reading. Very important. Now, number 3, respiratory quotient. Respiratory quotient. Make sure you highlight this because they're going to ask you what is the definition for respiratory quotient. What only thing you need to know about that is it's the unequal exchange of CO2 produced versus oxygen used. Number 3. Respiratory quotient is the unequal exchange of CO2 produced to oxygen used, right? We use oxygen and we produce what? CO2. So that usage and production is called respiratory quotient. It's called respiratory quotient. So what they're saying is, out of 250 mLs of oxygen that we use, 200 mLs of CO2 is produced. So when you do the math, the normal respiratory quotient is 0.8. Write that down. 0.8 is the normal RQ. The normal RQ. Now, don't confuse VQ and RQ. Okay? VQ is ventilation to perfusion. The RQ is the respiratory quotient. That's just saying when you live your life, you're going to use oxygen and you build or develop CO2. That's metabolism, right? Metabolism. And they're showing you exactly how much is the metabolism. About 250 mLs of oxygen in your blood. You use that and you produce 200 mLs of CO2 for every 250 of oxygen that you use, right? That's all they're saying. You don't have to remember that part. You just need to know that it's 0.8. If they say, what's the normal respiratory quotient? 0.8. You need to write that in. You need to make sure you have it in your formulas, right? Or your value, your normal values. And it's in that normal value paper I gave you. I gave everybody a normal value sheet that's going to last you all the way through your whole respiratory career. All right? And that's from the Krebs cycle. When you were in high school, they talked about the Krebs cycle, mitochondria and all. You burn carbohydrates, you burn oxygen, and you produce CO2. That's part of what you learned, if you learned it, and should have learned in high school. All right? But it's 0.8 right there for you to see. RQ 0.8. All right, last little bit. Gas exchange unit. I just did that on the board, but now you got it to write it down. If you want to write it down and take a picture of it, gas exchange units. What did I say? You have a normal unit, dead space unit, a shunt unit, and a solid unit. We just did that, yeah. Yeah, we did that. But that's it right there in words. Now look at what it says. Dead space unit, ventilation without or in excess of perfusion. So we got the gas, but we don't have the blood. That's dead space. Shunt is perfusion without or in excess of ventilation. We got the blood, right? But we don't have the ventilation. So that's a shunt, okay? You can think of shunt as shut. The alveoli is shut. Shunt, shut, right? If the alveoli is shut, then it can't pick up no oxygen, so that can help you remember shunt. The shunt is when the alveoli is shut. Shut the front door, right? When they say that, that's a shunt. All right, that'll help you. You'll never forget it, all right? All right, number 4, solid unit. The solid unit is no perfusion, no ventilation, okay? No perfusion, no ventilation. Now, the regional differences between these two, number 1 and number 2, very important. Regional differences. Regional means area of the lungs, right? Perfusion and ventilation is different in different parts of the lung. It's different, and there's reasons. I'm on number 1 in the area. Regional, like your region, this region of your lung, that region of your lung. But there are more ventilation to the bases of the lungs than it is to the apices. So there's more ventilation going on at the bases of your lungs than it is at the top. More ventilation? I would have thought that air rises, so it would have been more ventilation up at the top of my lungs. Okay, it says due to gravity's effect on the pleural pressure, so you'll be right. So how much? Like it says, it's more ventilation in the bases of the lungs than at the top. How much, Mr. McCarthy? It's 4 times more ventilation in the bases than in the apices. You need to know that. 4 times. That might be a question. How many more times is ventilation in the bases than the apices? You gotta know, oh, that's 4, right? You gotta know that's 4 times more. Why is it 4 times more? Well, due to the gravity's effect on pleural pressures, and on inspiration, the transpulmonary pressure is greater at the bases, right? When you breathe, the diaphragm drops and it sucks them lungs open. Strong down at the bottom, right? It's sucking that air in, right? What about the perfusion? There's more perfusion to the bases as well than the apices. And that makes more sense to me because blood is heavy, right? And gravity, basically just because of gravity. Gravity, blood drops, right? How much more is perfusion at the bases than at the apices? 20 times more. 20 times more. So you already know there's going to be questions. And finally, we already did this part, ventilation to perfusion ratio, VQ. Here it is right here. 4 liters of alveolar minute volume to 5 liters per minute of cardiac output. Now look, the ratio is 4 to 5 or 0.8, but a lot of people, RQ is 0.8 and so is VQ. So be careful. Don't get mixed up on those, because if they say, well, this value is 0.8, and it also does this, make sure you know which one they talking about, because both of them are 0.8. Okay, make sure you know which one they're talking about. But if you just do 4 to 5, that's good enough. That's good enough. All right, you have homework tonight. I'm gonna share my screen to show everybody what I'm talking about, so there are no questions about what I'm talking about. Let me share my screen. All right, in the module, I think I even made an announcement. Pulmonary mechanics, right here. Homework RT210 D, number 1 and number 2. Those are due by midnight tonight for attendance and for grading, because I'm going to grade it. Make sure I can see it. Don't just write anything. Oh, he just grading for completion. I'm grading for accuracy as well, right? So make sure you look in your reading, because it's all the answers are in the chapters. Okay, the chapters that they give you. If you ain't heard me say it, find it. It's in there. You have to really research hard and study hard for these classes, guys. So work on this. That's what's done tonight. The mechanics comprehension quiz right here, you can take that tonight, work on it if you want to. It's got some blasts from the past on it. It's got some blasts from the past questions that you might want to make sure you understand, right? I took a picture of the whiteboard yesterday, that spirograms and stuff. So that's picture 1 and picture 2. They're on there if you want to look at them again. Yesterday's live lecture is also here, okay? The classification, ventilation classification worksheet. I didn't get a chance to go over that today. We can go over that first thing in the morning. Well, not the morning, but tomorrow. Tomorrow we'll go over classification worksheet, and then we'll finish the lesson. All right, finish the lesson. There's only one lesson left, lesson number 5, which talks about the different types of shunts, I think, yeah. And so we'll finish that up and we will be complete. We'll start preparing for the exam. All right, you learned a lot today. If you missed today, you missed a lot. Look at the video, go back and watch the lecture as much as you can. If you have any questions, you can email me. But there is a lot of information that was covered today. Again, I just showed you the homework, showed you the comprehensive quiz. If you like to go look over that, I encourage you to look over that for reinforcement. It'll help you with stuff from the blast from the past. Don't forget, you have blast from the past, because you have that oral coming up soon. Before you know it, you'll be taking your oral. You must go back to A, go back to B, go back to C every day, and study a little bit from each one so that you don't forget. If I was to ask everybody right now, lay me out the electrolytes, everybody wouldn't be able to do it. Okay? So but you got to be able to do that, because it could be on a test. Also, this coming test, you will have 5 terms on there from that vocabulary worksheet, respiratory vocabulary from 11 through 20. Okay? You studied 1 through 10. I gave you 5 of those. The next batch will be from 11 through 20. So study 11 through 20 every day, because 5 of those words will be on the exam. Okay? Test it's in the syllabus. We on schedule. We on schedule for the test this time. Okay? All right, you are free to go. Have a good day.